lecture 22 of CS267. So this is going to be a two-part lecture, and it's going to be concerned with some variants of load balancing, also minimizing communication for the first part. So that's going to be the focus of this 40 minutes, graph partitioning. And I, of course, owe a lot of these slides to various different people. So what is graph partitioning? This is the looking like a very long summary of the lectures, but we're not going to cover all of these things in the same detail, especially some of those we're just going to go over very fast. The definition of the problem is simply given a graph, and I'm going to start it with an abstract wheel. I'm just going to call it a graph, as you've seen graph algorithms lectures, which is composed of vertices and edges and vertices both can be weighted. And the task is simply to partition this thing into k parts or p parts, if p is the number of processes, minimizing certain objective function and subject to certain constraints. And that looks awfully abstract, but it's actually very useful and flexible. We can define the vertices to be arbitrary tasks depending on our goal, and the vertex weights and the edge weights can encode certain information that are very valuable. So I should probably here's one example on how to group these into 4 processors, and this just simply putting 2 vertices at each node. And we're gonna think about a special case, which is a graph bisection version, meaning you're given a graph, you're just gonna divide it into 2 pieces. And the nice thing about graph bisection is you can generalize it to p parts by simply recursively doing it. So the original application is due to Kernighan. And if you care about the history of computing, you can look it up, look his name, and he wrote the book about the C. He's the K in the ALK tool you might be using for text processing in Unix standards. He coined the name Unix and various other things. And in fact, one of the prominent heuristics we're going to go over later this lecture is due to him and Lin. So load balancing and minimizing communication is primary motivation for our purposes. And we can define communication depending on the task. But a very good use case we will see repeatedly is sparse matrix times vector multiplication, something you have seen before. But it can be used in a lot of different use cases, as you might imagine. And it just requires some thinking about how to define the tasks and how to define the weights of the edges and vertices accordingly. And once those are properly defined, then the graph partitioning can actually do the job for you. So here's our motivating example, which is a sparse matrix vector multiply, where the sparse matrix is symmetric in this case. We're going to go over non-symmetric cases later. So we have 8 by 8 matrix, and we want to partition it into 4 pieces, let's say, and each one of these colors, the big circles, is a partition, and it's assigned to a processor. And you can see that the edges that are crossing across partitions is some sort of a metric for communication. What does that mean? Well, I am the processor who owns vertices 1 and 2. Well, all these non-zeros within that little 2 by 2 block, I don't need to communicate when I'm doing matrix times vector multiply. Think of there's a vector here and there's a vector in the output. I have everything I need for that part. However, for all the non-zeros that are outside the block diagonal, meaning those non-zeros here, for example, that go from 1 to 3 and 2 to 4, well, I don't actually have the other end. So when I'm accessing the source vertex, 3 and 4, whomever owns the vertices 3 and 4 need to send me the values on this vertex. Similarly, the green processor needs to send me the value corresponding to the 5th entry of the vector. Let's call the vector is x, and then I need to get x5. So that means that's the communication. If I partition this thing as good as possible. The goal is to minimize these parts outside the block diagonal that will create communication. That's in an abstract view. We're going to go into details. Let's say you did graph partitioning. How can you actually write the sparse matrix vector multiply? That's the pseudocode at the bottom. The thing to emphasize, the thing I wanted to emphasize here is now that we minimize this communication with graph partitioning, we need to do personalized communication, meaning I have to request in some way the vertices or the X3 and X4 from the red processor, and it needs to send those back to me. And from the green processor, I also, assuming I am the blue processor, I need to also request X5. So this needs to be personalized. Otherwise, I don't see any benefit of graph partitioning. And why is that the case? If the other processors blindly send all their data to me, then it doesn't matter what the partitioning is, right? This needs to be a two-phase process. When I'm requesting the exact vertex or vector values, they're synonymous because we assigned one vector value to a vertex here, and the owner of that vector entry needs to send it back to me. If I didn't do graph partitioning at all, and if the matrix was sufficiently unstructured, meaning there were non-zeros all over the place, in every single little 2x2 block here, if there was one non-zero, then I might be better off by just broadcasting, saying that, okay, I think I need every single vector entry. I'm kind of unlucky that I have a value everywhere in this row, somewhere within those subcolumns, if I project it down. And then at that point, there's no point in me asking for particular vector values. I just say, just broadcast all of it to me because I need so many entries. So that's something that needs to be emphasized. If you want to take advantage of the sparsity with graph partitioning, then you have to actually do this two-way communication of request and receive. Of course, you can do this with remote direct memory access using support that is inherent in languages like UPC++. Graph partitioning is provably exponential in some, okay, NP complete, actually. We don't know if it's exponential, but we strongly believe that is the case. What that really means is we need really good heuristics to solve this problem. So we cannot really solve the problem exactly. And luckily, we have a lot of them. And just to repeat the same thing, most of these, the lecture is on graph bisection, meaning you're separating the graph into two pieces, because you can actually choose the balance constraints accordingly and solve for effectively any P. Maybe not the greatest optimality, the greatest optimality, but good enough. Even if it's, let's say, 6 pieces, you can actually divide it into 2 initial pieces by bisection, where the first side gets a weight 1 and the second side gets a weight 2, and then recursively call these in the subpartitions and just rely on the graph bisection heuristic to get to any P pieces. It is really valuable to understand the concept of a separator when understanding certain graph partitioning algorithms. A separator is simply, can be defined in edges or vertices, but let's think about the edge case. It is a set of edges of the graph that separates the graph into 2 almost equally sized disconnected components, right? And in this example, what we're seeing is we can treat either the green edges or the blue edges as an edge separator. Whereas the vertex separator is analogous, except it's defined on vertices, which is a subset of the vertices that whose removal will disconnect the graph into 2 equal sized pieces. And given one, you can always choose the other, meaning if you're given a set of edge separators, you can define a proper vertex separator and vice versa. And why is that really important? Well, if I find a good separator, then I can actually, I partition my graph effectively. Then I just need to figure out what to do with the vertices on the separator, which side I'm going to assign them. And so the first part of the heuristics is I'm going to go very short, and I'm not going to give any examples for various reasons. One of them is time, and the other one is that this is mostly a solved problem. Let's say you don't have the graph structure, or you don't care about it. That looks like a little bit of a crazy thought, right? Okay, the lecture is about graph partitioning, and I'm not going to use the graph structures. So sometimes people call this mesh partitioning, and it makes a little bit more sense because then you can define let's say a regular mesh, two-dimensional mesh or three-dimensional mesh, and the connectivity is regular. Here you're given certain coordinates, x, y, potentially z, depending on how many dimensions you have, and you assume some sort of local connectivity between them. If xy is closer to x2, y2 in the spatial discretization, then they implicitly are assumed to be connected, so to speak. And why the algorithms work is actually somehow motivated by this theorem by Lipton-Tarjan theorem, which is if you have a graph that's planar, you can always find a separator where the size of the separator is on square root of the number of nodes times some constant. And that's actually a pretty small number. And that works with any planar thing. And why does it have to do with nodal coordinates? Most of the things that work on nodal coordinates are planar graph implicitly, because you're defining xy coordinates. And if you can define xy coordinates and think about local structures, then you get something planar. The algorithms of these two of those that are well known as inertial partitioning or geometric mesh partitioning. Again, we're not going to go over the details about how they work, but all you need to think about is the edges are implicit, and you don't need to worry about those. The coordinates are the input. The coordinates of the vertices are the input to the graph partitioning algorithm. These algorithms, because they don't care about the edges, and the number of vertices are generally much smaller than the number of edges, are very efficient in terms of computational time. And they work very well when the graph comes from a physical model, where the actual connectivity matches the proximity in the spatial dimension. But if the connectivity is not spatial, like in this snake-like figure you see at the bottom, then the result you will get can be catastrophic, right? So you only used when the problem actually fits the definitions or fits the constraints, assumptions of the algorithm. Now here's the actual graph part, where you're given a graph with arbitrary connectivity structures between vertices. And these are, think of them as networks you can find in biology, in internet, social networks, or any other structure, epidemiology. So the first heuristic we're going to go over is, again, due to Kernighan-Lin and Kernighan. Lin is another person. The way it's initially defined was fairly expensive heuristic, but then Felicia Metises improved this to be a linear in the number of edges. And so it's actually became feasible. And one of the reasons we're going over this heuristic, even though almost no software directly just implements this, is it's used as a subroutine for the so-called big idea in graph partitioning, which is the multi-level partition we're going to see in a couple of minutes. And this is really about initially starting with some partitioning. Again, think about bisection, partitioning into two pieces, which is balanced according to the balancing constraints given by the user. And for now, just assume that we want them to be equal sized. Then finding subsets of vertices from partition A and partition B that will allow us to swap them, so that the partitioning objective goes down. So it's an iterative algorithm. And what we want here is we want to find subsets that are of the same cardinality in part A and part B. Otherwise, we would be violating the balance constraints, right? And we have a couple of definitions we need here. And I'm going to give just enough for you to understand what's going on. Let's say you have already a cost of your graph partitioning, the number of edges cut, AB, and you want to quickly find out what would be the cost of graph partitioning if you swap some vertices across partitions. And for that, you need to keep track of a couple of things. One of them is the external cost of any vertex in part A, which means, what is the number of edges that are going crossing from A to the vertices in the other partition. An internal cost is the sum of the edge weights from A to the vertices also within A. And why do we keep track of both of them? Because once we move A from part A to part B, partition B, well, we're gonna save all the external costs. We're no longer gonna be cutting those edges that are capital EA. However, we're gonna be incurring cost due to IA. So the difference is really what we gained in terms of minimizing the number of edges that are cut across partitions. So we can always decide to swap two vertices, and we can define the new T as the old T minus the difference that we just defined for the A that's moving, difference that we defined for the B that's moving. And now we accidentally actually double counted, in fact, the cost of the edge between A and B, as if, because we don't know what the other vertex that's moving from part B, for example. We also accounted for the cost of the edge in between these two, but we have to subtract it out. So in some sense, that's defined as the gain of swapping A and B. And the code that looks awfully scary, and we're not going to go over this, luckily, is iterative. The point here, the reason I keep this in the slides is simply it's a, the one thing that's worth mentioning here is we don't actually immediately swap vertices. What we do is we consider pairs of vertices to be swapped and then figure out at what point we got the best gain in terms of minimizing the communication cost. And then we roll those back up. We find those pairs of things that are worth swapping, and then we make that swaps permanent. So really, it's all about marking nodes that are worth swapping and figuring out which pairs of swaps are proving to be the best gain in terms of minimizing communication, committing those things, and then calling it done in terms of the iteration. And we're going to go back and do it again. So we're going to give a simplified execution due to the improvement done by fiduciary metices. Again, this is in some sense a very simplified execution, but it's going to give you a much better intuition than looking at the code. So let's say we have two partitions of this 8 vertex graph, and the vertices are labeled with the alphabet letters. And what do we see? The numbers next to each node or vertex is the gain if we swap it. If we move that, actually not swap, because we're not considering the swap yet, if we move that vertex to the other side. So we consider the highest gain in this heuristic, which would be given if we moved G to the other side, right? So we just moved it. And now we have to recompute the gains of its neighbors, because that's the crux. As soon as we tentatively move a vertex, then the gains are affected because of that move. Well, luckily in FM heuristic, we can actually do this update only by looking at the neighbors of G. So this neighborhood structure update, meaning don't look at every vertex, because the only things that can actually get affected by moving G to the other part are G's neighbors, is what gives this algorithm order E per iteration time. So we look at its neighbors, we recompute the gains of its neighbors, then we have to now choose a vertex from the other side that will give us the best gain, which turns out to be D. Because every other vertex, if we move it to the red side, actually is increasing the partition cost. So D is the only one that gives any improvement. So we tentatively mark D. Now our new cut size is 4 after this first tentative swap. But what that means is, let's say we move G to the other side and D to the red side. And then we're going to keep doing this thing. We're going to find another vertex with the highest gain from one side, F. And then we're going to find vertex with the highest gain from the black side. And we're basically tentatively marking them as if they moved to the different side. So that's how we mark them with hello vertices. Now, surprisingly, the cut size have increased after our second swap, but that shouldn't discourage us, because that might be a local, the previous one might have been a local maxima. And it's possible that even after this increase, by continuing this algorithm until we mark every vertex tentatively swapped, we might actually get a cut size that's smaller than 4. We don't know, but unfortunately, it's not going to happen in this example, but that's all right. And at some point, of course, we have no vertex pairs that haven't been considered. And now we look back on the execution, meaning we started with a cut size of 8, and we went to 4, and from then on, it went up. So the optimal in the sequence is after the first swap. So what we do is we mark that swap as permanent. We do all the changes that happened after that, undo them. And that's basically the end of our first iterative improvement step. Now we're going to do another improvement step starting from this new size 4 cut. Of course, first we're going to recompute all the gains. We're not going to show the execution again here, but we can actually get a different execution because we recomputed all the gains. And it's quite possible that we're going to get some gains, but if we don't, then the algorithm finishes. If that iteration, there is no better partition, then the algorithm is done. So that's essentially all there is. It can escape local minima, as we said, and Kernighan and Lin, when they tested this on very small graphs, they got convergence in after a couple of iterations, 2 to 4. It might not be that good in large graphs. So that's one of the reasons why almost nobody runs Kernighan-Lin or Fiducia Matrices heuristic in graphs with millions of vertices. But it's actually used as a subroutine in the big idea we're going to see in a couple of minutes. Another approach that is used to be very popular and still is popular in certain areas is the spectral bisection. Here we don't actually look at the combinatorial algorithm. You can think of the Kernighan-Lin heuristic as a very combinatorial iterative swapping. Spectral bisection looks at a matrix that's associated with the graph called the Laplacian, the graph Laplacian. You might have heard about this. And this Laplacian is simply this matrix where the diagonal entries are degrees of the nodes, like the diagonal II is the degree of node I. And if there's an edge, if from I to J, then it's marked with -1, everywhere else is 0. So it's almost like a adjacency matrix, except that the only entry is -1 in off-diagonal entries, and the diagonals are the degrees. You can define this as a multiplication of the incidence matrix with its transpose, but no need to go there, frankly. You can just define the Laplacian directly on what it is. So here's one example of the Laplacian for a regular 2D mesh. As you can see, just whenever there's an edge, there's a -1, and all the diagonals are the degrees of the particular vertices on that notation. So it's the only thing we really want to emphasize, I want to emphasize here is this is mostly based on the eigenvector associated with the second eigenvalue. So if you look at the Laplacian, you can prove a lot of nice things. One of them is it's all eigenvalues are non-negative, and the multiplicity of the smallest eigenvalue is really the number of connected components. If your graph is disconnected, let's say into 5 pieces, you'll see that the smallest eigenvalue, which is 0, will have multiplicity 5. And we've seen this in spectral clustering and ML part 2. And you can go back and rewatch this and why this is the case. So that's one motivation. So therefore, it's kind of a useless eigenvector for our purposes, but we can use the second smallest one, which is known as the Fielder vector, the eigenvector that's associated with the second smallest eigenvalue is the Fielder vector. And simply these algorithms are basically look at the Fielder vector entries. And for each coordinate in there, if that coordinate in the eigenvector is negative, then it's put in partition 1. If it's positive, put it in another partition, and then we recursively do it. So this is another recursive bisection algorithm. I'm not going to be able to spend too much time on the whys of this algorithm, why it might make sense, but another concept that's worth mentioning is that the eigenvalue, the second eigenvalue, is considered the algebraic connectivity, and one can prove certain statements that the physical connectivity is related to this algebraic connectivity. Graphs that are less connected by other definitions have actually a smaller algebraic connectivity in the spectral space. So there's some reason why this algorithm makes sense in practice. Okay, that seems all great, but how do we compute the second eigenvalue and the eigenvector associated with it? Well, there we go and implement something called the Lanczos algorithm, which is an iterative algorithm that does sparse matrix vector multiply. One can ask itself, why did we do this thing? Because our initial motivation for studying graph partitioning was to be able to partition the graph so that we minimize communication in sparse matrix vector multiply. But just to be able to do that, we now need to do sparse matrix vector multiply. So that's one of the reasons why people call this graph partitioning problem, at least some of the algorithms, as chicken and egg. You're trying to, you're using this thing to improve the performance of something, but you need that something to solve the partitioning problem. However, that's a little bit of oversimplification because the applications of graph partitioning go well beyond the sparse matrix vector multiply. In fact, one can argue that sparse matrix vector multiply is repeatedly used as a motivation because it's easier to explain, but it's actually not all that commonly used application of graph partitioning. There's many better applications of this tool. So let's get to the multi-level big idea, which is the popular software that implements graph partitioning, at least the most popular ones, use this multi-level acceleration. And the whole idea is based on the fact that heuristic like kerning and Lin might be good, but they're unscalable to really large graphs. So how can we actually make them work on large graphs? Well, what if we got a graph that is smaller in size, but topologically look awful like the original graph? And we partitioned on that so-called coarser graph, coarse approximation. Capital GC is what we're going to use it for the coarse graph. And if we can solve the graph partitioning on GC, we can project back to the original graph. Well, what if GC is too large? Well, we do this recursively. So here's a picture. You start with a large graph. It's called a V cycle for obvious reasons. From the picture, you can see. And we coarsen it repeatedly until we think that the thing we get at the bottom, the coarsest graph, is small enough to be solved efficiently by some sort of heuristic like kerning and Lin or faster execution FM. Well, okay, we solved it there to the best of our abilities, and now we're going to project it back. After each projection, we have to do we do more iterative refinements here, meaning because we are projecting back a coarse graph to a finer graph, it's possible that this cut is not optimal. And we can improve this thing by another iterative swapping, yet another variant of kerning and Lin, or different coarsening algorithms. In fact, we're going to see two different multi-level algorithms. So one of them is going to be iterating and improving with kerning and Lin. The other one, which is a multi-level spectral algorithm, will just basically interpolate the eigenvectors entries using a very fast heuristic. So that's essentially what we said. You can define the coarsening in many, many different ways. And one way to define coarse graph is to find matchings between vertices. A matching, we were supposed to see this in graph partitioning lecture, but there was no time. But on a graph is really a subset of edges is a matching, where no two edges share an endpoint. So you're trying to match vertices actually, and a maximal matching is a very local algorithm. This is similar to, I don't want to spend too much time telling the difference. Maximal is just a local optimum. You're given a matching, you cannot add more edges and improve its cardinality. It is not a global optimum. It doesn't mean it's the maximum among all possible matchings in a graph. It's all it means that you're given a matching, you cannot improve it without deleting all the previously considered edges. And for that, simplicity comes with really fast algorithms. So a simple greedy algorithm will compute a good maximal matching. So, for example, here's a maximal matching, right? The subset of the edges that are part of the matching are color-coded red. And they are indeed a matching because they do not share any endpoints. There are some vertices that are left, like 8, but that's okay because this is a maximal matching. Now I'm going to define my coarser graph as groupings of endpoints, right? So the order of the coarsening here, so to speak, which is how many, what the factor of the factor that the vertices are going down is only 2, or in fact less than 2, because there's some unmatched vertices. But that's okay. That's maybe a slower coarsening. And we're going to collapse these endpoints of each edge in the matching into one big vertex called the aggregate vertex. And then we're going to get a different graph based on that. So that's all there is. And here's a slightly complicated way of defining it. Here's a pictorial way of doing it with sparse matrix products. Assuming you have a matching, like the one I show at the bottom, the aggregate one is 1, 2, and so on. And you can just define an auxiliary matrix where each row has a 1 for the fine vertices that are going to be part of that aggregate. So A1 is here, A2 is here, A3 is the third row, and multiply that with the original sparse matrix that represents the graph, and the transpose of the same auxiliary matrix, you'll get the coarse graph. And that's assuming you have a matching. So you can basically apply this matching at each layer, coarsen, and keep going, and you're going to project it back by just doing this backwards. One thing I'm not going to go over is, okay, how do you do this in spectral case? This idea works if you do work on the non-spectral multi-level algorithm. If you have a spectral algorithm, what does it mean to project back an eigenvector? So, and there you use the improvement. You cannot use the Kernighan-Lin of swapping. You use something called the Rayleigh-Quotient iteration. And I'm just going to go forward there, which is simply a warm start of an eigenvalue finding. Right? You're just going to start with the eigenvector from the previous course level and use interpolation, and then iteratively improve it with this algorithm that is described in this picture. Since I have only 5 minutes, I'm going to leave it at it and talk about some things that I find slightly more pragmatically valuable. One is, of course, available implementations. There's no need to go over this slide. You can go over it by yourself and click on the links. Or if some link is broken, you can certainly Google. The most powerful tools, versatile tools, are multi-level tools. Metis and PyMetis are serial and parallel versions of this thing. You should keep in mind that PyMetis is not exactly implementing Metis algorithm. If you plot the performance of PyMetis with the number of processors versus the partitioning quality. For a fixed graph, you'll see that its partitioning quality will go down as the number of processors increase, and that's because it actually uses a locally biased algorithm that relies on the fact that this whole thing is a heuristic and tries to avoid performance issues by cutting corners as it parallelizes. And that, of course, comes at the cost of quality. However, I just want to mention an issue with graph partitioning. So let's start with actually this picture. Here's our sparse matrix. On the left, this is this 10 by 10 sparse matrix. We can represent each row or column with a vertex. And we can, as before, we can put each edge as each non-zero as an edge. Okay, now what is the cost of graph partitioning if we partition this into two processors, P1 and P2? The P1 gets 5 vertices, P2 gets 5 vertices. Let's focus on one thing. Here, what we're seeing is V7 is on one side, and it has an edge with V4, it has an edge with V5. Okay. Now the argument goes that since the endpoints of these edges are in different processors, I need to communicate them. But that's not really realistic because given that the communication only requires V7, so the processor who owns V4 and V5 needs V7, but it doesn't require V7 twice. It only requires it once. Any good implementation would be able to, in some sense, bundle the request to V7 and only send the X7 entry once. But how can we model this? Clearly, the graph is not modeling it correctly. So it brings us to hypergraphs. And a hypergraph is a generalization of a graph where the edges are no longer binary. They can connect more than two endpoints. They're also called nets. And here what ended up happening is there is it looks very crowded here, but bear with me for a second. Then a hyper edge becomes, for example, rows, and the columns become the nodes. So when you look at a hyper edge, whether it's cut or not, you can count it correctly by saying how many different parts is connecting. Now, of course, this is a bisection problem, so it's somewhat of a dumb question because it always connects two parts. So the connectivity of every hyper edge in this example is 2. But if you were looking at a k-way partitioning problem, where there is, you're dividing it into k pieces or p pieces, the connectivity of a hyper edge would be the number of parts it's connecting -1, which would be the accurate description of how much communication is needed when someone needs that entry. So that's all there is. And using this right model in hypergraphs, you can get much better quality. And there's good hypergraph partitioners out there. One thing that we need to focus on here and remind people is hypergraph partitioning is almost an order of magnitude slower than graph partitioning. So only use it when it really matters. And when does it matter? For example, it doesn't matter really all that much when you're trying to partition a regular graph like this. Yes, it will give you a little bit of improvement, but that's not why we do hypergraph partitioning. We do hypergraph partitioning when the rows, the connectivity structure of the rows or columns are irregular. Because when they are regular, okay, we might be overcounting with this example, but each row is overcounting the same amount. If each row had the same regular structure that you would see in a two-dimensional mesh, then graph model will be making the same mistake proportionally for each row. And the end result would not matter all that much. However, if you have a skewed graph, meaning some row has 1,000 non-zeros, some row has 2 non-zeros, and so on, well, then the mistakes done by graph partitioning in terms of overcounting matter significantly. In one case, we would need to count only 2, ended up counting 100. And that's a huge difference. So graphs that come from social networks, from a lot of biology applications, where there is a skew in the number of non-zeros in rows and columns. There, hypergraphs might actually matter quite a lot. And with that, I think I'm gonna, there's other reasons why we might be using hypergraphs to account for non-symmetric graphs. And as another example. And there, I'm just gonna basically end it here. Here's the summary slide for graphs versus hypergraphs and some of the tools that you might need, and give it to Kathy, the control of the slides to Kathy. I think I'm 1 minute over.
Thanks very much, Aydin. Let's see. Oops. All right. And I'm going to talk about something that's related to load balancing, but where you don't have enough information usually to use graph partitioning. So let's see, which, as I said, is used for many other things too. Right. So I'm going to, as I said, talk about load balancing, and you'll see there's a bit of a connection, hopefully at the end of this. I'm going to talk, though, more about the dynamic case where you have to make, you can't sort of do something offline, something more static, and go and analyze your computational graph. So just to back up a minute, to think about reasons that you might see, I'm going to try to give you some practical hints about your final project in terms of analyzing the performance. Remember that we really want to see a very thorough performance analysis of whatever you're doing. So sometimes you're going to find that you don't get the kind of scaling that you want. And the question of why that is the case is really important to try to answer in your write-up and in general when you're writing papers about parallel computing. So you could have a serial bottleneck. You could have insufficient parallelism, which you would say, well, a serial bottleneck could be an example of insufficient parallelism, but it may just be that you've got, just don't have enough work items to do. And you may have too much overhead from the parallelism. That is the cost of, for whatever reason, what you're doing. For example, the amount of work you're doing is too small in each unit, each thread or something. You have poor locality, or you have load imbalance. So let's talk about the load imbalance case a little bit more. So if you're looking for load imbalance in your application, and let's say you're writing an MPI application or something with barriers where it's a little bit easier to see this, you can, kind of distinguish the different cases of performance problems between, on the left picture, you've got good load balance. All of the processors are doing the same amount of work. They hit the barrier at the same instant in time, but they have maybe a slow barrier. And on the right-hand side, you have a serial bottleneck, which is an extreme case of load imbalance because you've got a lot of area here underneath these threads where lots of the threads are idle. And the middle is somewhere in between in terms of load balance. But the point is that, that it can be hard to tell the difference between these two if you're not careful about how you're measuring things. There are a number of tools that NERSC provides for performance and debugging. I think you've already used some of these, but here's a link at the bottom to look up the latest things. And when you're measuring load imbalance, one of the kind of common rookie mistakes is to measure the average performance of something. And then you don't really know whether you've got a load balancing problem or you've got some other kind of a performance bottleneck, whether it's communication overhead or something else. So you don't want to just average across all of your processors when you're looking for performance bottlenecks. You need to look either at the individual values or look at a histogram or something like that of what the running times are. And you can look at sort of the effective load imbalance by looking at the maximum minus the average time over the average time. That tells you sort of how much, what's the percentage of overhead that you're spending in load imbalance. And be sure that you have to be very careful about where you put your timers relative to where you put your barriers. And it's often the case is that people don't see load imbalance because either there's an implicit barrier in something they're doing, such as a reduction operation or other collective, or there's something going on where they've accidentally put a barrier synchronization, for example, in the middle of some function call that they didn't remember, or they put it on the wrong side of the barrier. So you have to really be very careful to make sure you put the timers around the barriers and separately from whatever computation you're trying to measure the load imbalance of. It's especially gets to be subtle if you are writing applications that are not using barriers at all. And even worse is if you're using spin locks, because a spin lock is going to look like computational work from the perspective of any one of these performance tools. And so from your own standpoint, you need to make sure you're measuring the time spent in a spin lock. All right, so let's talk more about load imbalance though. What are some of the reasons that load imbalance come up in your application? You have a bunch of tasks that you're trying to do on your parallel processors. There could be variable costs to each one of those tasks. They take a different amount of time each. The number, I should say, of tasks may be highly variable in some part of the code, or the structure of the dependencies between the tasks can cause serial bottlenecks or things that cause problems with terms of scheduling. Now you can also have machine variability that leads to load imbalance. Here's a couple of classic examples of this. And then the left-hand side is a best paper award paper from supercomputing in 2003 called The Case of the Missing Supercomputer Performance. And it was looking at a code that they thought was running fairly well, except that it turned out that there was some reason that it wasn't giving the absolute performance that they were expecting. And when they looked at it across all the nodes, and this gives you a good idea why you don't want to average, so the x-axis here is nodes, there are these spikes in the running time. And it turned out there were operating system daemons that were running on every, whatever it is, every 16, 30-second node, something like that. And those were, say, collecting some information, and that was causing this highly variable performance. What was going on here with, processors 900 through 950 or whatever, I'm not quite sure about that one either. But the basic problem was things that the operating system was doing were slowing things down. On the right is actually an example of hardware variability, and this was taken on a machine that, once it was presented to the people, I think this was actually at Oak Ridge, it turned out when they investigated what was going on in these particular processors with the spikes, and by the way, there were two different executions here of different sizes. The blue execution is completely independent of the red one, but the point was that they looked at how the processor IDs were mapped onto the nodes in both of these executions, and it turned out that there were some processors that had memory that was starting to fail. And as with disks, which we're kind of more familiar with this issue with disks, as they get bad, as they get old or whatever, and they start to have failures, then the error correction software that's running, or in this case, in the memory system, the error correction hardware that's running can actually slow things down. And so these memory chips on some of these nodes were starting to fail, and that caused these ECC memory faults to be corrected. So the program was running correctly because the hardware was correcting the errors, but taking a lot of time. And we can also see this on the cloud. I talked about this last time, although if you're using sort of an HPC instance of a cloud where you've got dedicated processors, this is less of a problem, but we see these long tail effects on applications that are running other more kind of generic standard parts of the cloud. All right, so what can we do about this? Well, we can try to statically divide up the work into pieces, and that's useful if you've got enough information in advance of what you're going to be doing, or you can dynamically try to reschedule things. And by the way, an observation and an important point I want to make sure you take away from this lecture is that load balancing and locality often trade off. There's often a trade-off between them. So for example, in order to minimize locality, the optimal solution might be to put all of your work on one processor so there's no communication. If you want to load balance it, that typically is going to involve spreading things out more, which causes communication between those tasks that you're spreading out, but also the work itself of load balancing things. So that it's not always obvious that load balancing is the most important thing to do, even if you measure that you have some load imbalance. All right, so we're going to talk about three cases. The first one is where you have a bunch of independent tasks, such as a loop that you're trying to schedule, and there's no loop carried dependencies. So within that, there's a few different cases. We can look at loops in which all the statements, the loops that are nested within have a fixed loop bound, and there's no conditional. So what this means is that every iteration of this outer loop is going to have the same cost. And then in the right too, you can have more and more variability conditionals and things like that, where maybe you know something about the different costs of the iterations, or on the right hand where you don't have any idea until the loops execute what their cost is going to be. And so this is more of a pictorial version of those three different cases where you've got equal sized tasks here on the top, different sized tasks, but you know something, you can estimate for somehow what the different costs of the executions are. This might come up in something like an adaptive mesh refinement algorithm where you've got different block sizes that are spread out over the processor, and you can estimate the cost of each task associated with the blocks because you know what the size of those blocks are. And so that may or may not be exactly the right it might not correspond directly to the cost, but it probably gives you a good estimate. And then in the hardest cases where you don't know anything about for how long anything is going to take. Now, when we've got statically known ones, we can try to solve this as a bin packing problem where we've got a fixed number of processors with a fixed amount of memory, say, on them, and you're taking each task, which is going to require a certain amount of memory, and put that onto each one of these, put each task onto one of the processors. And just to be clear, almost every problem that we come up with in the scheduling domain, as with the graph partitioning domain, is going to be NP hard. And so that means in practice that we only know of exponential exact algorithms, and will in practice tend to run approximate algorithms. Now, there are some important easy cases that come up, such as if you've got a monotonically decreasing cost for each of your tasks, which is not unusual to come up in certain cases. Maybe you're searching something like in a game tree. Then you could use some kind of a zigzag pattern where you put these linearly across the processors, but make sure when you get to the second row of them that you flip it over so that the one that got the smallest task the first time will get the largest task the second time through. So what if we don't know anything about the estimates? So in the middle of the execution, these things are going to change. So one of the things, one of the oldest algorithms in here, and you can see it goes back to 1986, is an algorithm called self-scheduling. This is just putting all the work into a task queue and then pulling it out and executing it on each one of the worker processors. This works well on shared memory machines. It can also be implemented, though, on distributed memory machines, although the question of whether you're going to centralize the queue will come up. But here we'll look at the shared memory case for a minute, and that's what the results in this paper, which has theoretical results as well as experiments, were about, is the shared memory case. Now, it turns out that it's often the case that you don't want to just, that the tasks that are in the queue, even if you're not starting full operating level system threads, every time you pull one of those tasks out, that the cost of accessing that queue and the contention for the queue, if each one of those tasks is very small, is going to have too much overhead. And so the next obvious thing to do, and you see this even in OpenMP in terms of the kinds of primitives that are built into OpenMP, is to take a chunk of some fixed size K. And so there's a paper that talks about the theoretical analysis also behind this kind of chunk self-scheduling algorithm. And it will allow you to reduce the contention on the queue, for example. And so what happens, though, if K is too small or K is too big? Well, if K is too large, then you lower the contention overhead of accessing the queue because you're going to get a big chunk of things off, but your finish time can be very uneven. Whereas if with smaller chunks, you can have much more even finish time, but much more contention and overhead for accessing the queue. And so, and I'm kind of rolling all of the costs of sort of pulling something out, copying the data, whatever you need to do, moving into the cache as examples of that overhead. So this is why picking K can be a little bit tricky. So that led to the idea of guided self-scheduling. And this is due to Cook and Polychronopoulos. And the idea with guided self-scheduling is that at the beginning of the execution, you've got plenty of sort of work ahead of you that it's okay to take big chunks off of the queue. And as you get closer to the end, you want to make sure those chunks get smaller because you want all of the processors to finish together. And so you don't want them taking big chunks of work when you're near the end of your execution. So in this case, the chunk size K is the ceiling of the remaining work divided by the number of processors. And so that's the way guided self-scheduling works. Now, even on shared memory machines, and certainly when you get to distributed memory, you may want to privatize the queue, meaning that you might want to give every processor its own copy of the queue, or its own partition, I should say, of the queue, where you'll only have, any task will only live in one of these partitions, but it may be, each processor will have its own queue. Why would you want to do that? Well, you still need to lock your queue in certain ways if you're going to have other processors accessing that queue, which will come up here, but you can at least often do the accesses with much less overhead if every processor is, on average, it's only accessing its own queue and it only looks at another queue when it, for example, runs out of work to do. So that leads to this idea of task stealing. So you always execute off your own queue unless it's empty. And then if it's empty, you steal from another processor's queue. And when the question of how many tasks you steal gets back to the question that we just talked about. So things like guided self-scheduling might come into this, or some general heuristics for basically shrinking the size of the tasks as you execute. You certainly want to get at least chunks of tasks off of other queues if the tasks are relatively small in terms of the amount of work. And the other question is, which one do you want to steal? And typically when you're implementing one of these task schedulers, these task queues, you want to always execute your own from the top of the queue or the top of the stack, like it's a last in, first out implementation. And so why is that? Because that's the task that you're pulling out is going to be related to the most recent thing that you executed. So this will typically give you better locality. It's basically the way the program stack executes in a recursive program. It's just going to execute. So you're kind of treating this now as a program stack. So that's usually the right thing to do locally. However, when you steal work, you typically want to get the oldest thing from the queue, not the youngest thing in the queue. And the oldest thing is, and that's because the oldest thing is likely to have more work associated with this. If you assume that the computation is some kind of a tree of tasks that are executing, if you pull one of those tasks from the top, it's going to have a bunch of children underneath it. And so moving that over is going to be a better idea than moving something that was near the top of that queue, or I guess the bottom as it's shown here, but the youngest thing on the queue. Okay, so then this is about this locality issue for executing the local ones. And then when you're stealing, as I said, you want to steal something that is one of the older things to get more work. Okay, so now the other question is who to steal from. So once you've decided you're out of work or you're close to running out of work, you may want to amortize the cost of, or overlap the cost of getting the work. If you're getting close to running out of work, then you can look at your nearest neighbors, or you can look far away. And so there's advantages and disadvantages of these as well. Looking at your nearest neighbors, if you've got an algorithm that has a certain level of locality between the tasks, then looking at your nearest neighbors may be the best thing to do for that locality. Sometimes the tasks don't depend at all, don't have any communication between them. If you grab things that are farther away, that is often better for load imbalance, because if there's a few tasks, processors that start running out of work, they're going to be stealing from each other and then get less and less work in that community. And so stealing further away is likely to kind of spread that distribution out. Okay, so now there's a nice theoretical result in here. And this is getting around the fact that these problems tend to be NP hard. And this is using randomization to get around this idea. And the basic idea is the classic balls and bins argument. And it says that if you've got some number of bins, let's say P, where the number of P is the number of processors now, and you've got a certain number of tasks. And the question is, how do you want to throw those balls into the bins? And you can prove that with high probability using randomization, that if you throw n balls into P bins, that you get the following bounds. And the one that you really want is on the left, which is n is greater than P log P. And by the way, that's going to also come up as a nice sort of practical rule of thumb, which is if you're dynamically load balancing thing and you have fewer than log P tasks per processor that you're load balancing, you probably don't have enough work to do, and the cost of load balancing is going to end up being a problem in your experimental results. But here's a theoretical result that really kind of gives the same intuition, that says if we've got n over p log p, then the total running time is going to be n over p, the optimal, plus this term that is due to the the uncertainty in terms of the randomization. But this is actually optimal with high probability. So this is pretty close to being, this term on the right is pretty small. So there is another term in here in this result. If n is actually equal to p, things are a little bit worse then, of course. Now, there's lots and lots of scheduling algorithms, and I found this kind of poster online for some of the references to it. And I had, as I said, kind of two purposes of the lecture today. One of them is to give you some practical ideas for what to do if you've got load balancing problems that come up in your final project, how to measure that, how to think about it, and things like that. But there's also, if you've got a particular load balancing algorithm, it can be hard to navigate the space of related work to try to figure out which are the papers that are most important to you. And so I'll try to give you a little sense of what to look at. So far we've been talking about this sort of list scheduling where you've got a list of items that you need to schedule. There's no dependencies between them. You're just trying to figure out how to minimize the amount of minimize the load imbalance at the end. So the second case now comes up when you've got dependencies. So now you've got one task that produces, say, 3 other tasks, and that one of those tasks may produce some other tasks. And we can either have a tree of tasks, which is very common, or you can have a directed acyclic graph of tasks. So in this, we can look at now the task dependency spectrum. Before we were looking at the task cost spectrum, that is, what do we know and when do we know it about the cost of each one of the tasks. And here we can still have that variable cost of each one of the tasks. They're shown here as equal sized tasks, but because now we're looking at a second issue, which is, are all of the tasks ready at a given point in time? And or is there some kind of a pattern between them, such as a chain where there's a sequence of things that are dependent on the ones before? That would come up in a lot of physical simulation problems where you've divided up the domain, you've done domain decomposition, each processor is working on a particular physical region, and then it's mostly dependent on the ones before it, but it may be dependent also on, say, the one to the left and the one to the right or something like that. Trees are very common, and we'll talk more about tree search and when you've got computational patterns that are related to divide and conquer trees. Those come up, and we can have both an in tree. This is an out tree where one task is producing a bunch of others. There are also cases that come up in linear algebra with something like Cholesky or LU factorization, where you're kind of all waiting, the bottom of task at the bottom right is waiting for all of the things that are incoming to that, and that would be an in tree. And we can have a general DAG as well. And sometimes we have no idea what the task structure is going to look like ahead of time. If you know something about it, you may be able to, for example, run a graph partitioner on the graph and use something that's weighted that says what the cost of each one of these tasks, or even trying to minimize the data movement between them, which we'll also talk about. So these tasks, in terms of tree search algorithms, search problems are often very expensive. So these come up in things like playing the game of chess, or this simple version, which is maybe the most over-published parallel algorithm in the computer science literature, which is the n queens algorithm. If ever you are looking for a kind of trivial example, you've just got n queens on your n by n board and trying to figure out what are the optimal layouts. But more practical problems are things like optimal chip layout, robot motion planning, some symbolic problems, Grosvenor basis applications, computing phylogeny trees and things like that. These are projects that some of my students worked on many years ago. So here we've got our tree, our game tree search, and we have different types of nodes. We've got the terminal nodes that can be either a sort of a successful node, or the goal node, or a non-goal node, the blue and the orange here, that are all the leaves of the tree. And then the internal ones are the non-terminal nodes, the green nodes. And just to remind you, and I think this certainly comes up in graphs, but it can also come up in trees. We've got depth first search, where if we've got a stack, for example, and we're putting things on and pulling them off in a last in first out matter, then we're going to end up with a depth first execution in serial. Whereas if we've got a queue, a FIFO queue and we're always pulling off the oldest thing on the queue, then we'll end up with a breadth first search algorithm. That's what we get in the serial case. So this is just kind of reviewing those sort of execution strategies on a tree or a more general form of a graph. In a graph, you have to be a little bit more careful about the fact that two different paths can run into the same child node, and so you have to mark things or something like that. So in a game tree search, we can use various types of algorithms for or approaches for expanding that tree. A simple backtracking search might be searching all the way down to the bottom and then going back if you don't find a winning board. Branch and bounds, as you keep track of, is a way of sort of cutting off the search by keeping track of the best solution you've seen so far and cutting off subtrees that are guaranteed to be worse than that. Iterative deepening would be somewhere in between a depth first and breadth first search, where you sort of go depth first kind of to a certain level and then fill that all in, giving you the breadth at that particular level. And so you choose some bound on the search depth in order to execute that. So these are all just different strategies for unfolding a game tree, and that looks like this recursive algorithm. So what happens if we do this in parallel? Well, let's consider something like backtracking search, where we're just going to go depth first down the tree, but now we're going to do it in parallel. So for example, each processor is just going to go down one part of the tree. And so if we do something very naive like static load balancing, on the left-hand side here, you see two processors where the magenta processor gets the left child, the cyan processor continues executing then with the right child and gets a lot more work to do. And even worse, if we have four processors, some of the processors only get a couple of nodes to evaluate, and the cyan one still has a very large chunk of tasks. So in general, static load balancing does not work well on game tree search because the structure of the tree isn't known in advance. If you knew the structure of the tree, you'd know how to win the game. So in terms of theoretical results here, actually the same balls and bins argument can be used, and the same techniques that I talked about in terms of self-scheduling and things like that, or work stealing, can also be used in the context of a tree. Even in the non-tree case, there's just a couple of other extensions I wanted to mention here on this slide that are theoretical results that also can be important in practice. One is that rather than just throwing a ball randomly into bin, that is throwing a task to a random processor or stealing from a random processor, you can actually throw D times. So for example, if you throw it twice and you look for the least loaded bin, if you're pushing work away, or if you are stealing, you randomly look at two other processors and pick the one that's the most heavily loaded, you can prove that gives you better, even in a theoretical sense, that gives you better load balancing. And then Karp and Zhang showed that this idea also applies to a tree of unit cost tasks, and where the parent is done before the children and the tree is unfolding dynamically as in a game tree search. So now what happens with things that are not fixed size tasks? And so Charles Leiserson and Bobby Bluma proved that you can use this on a fixed task tree of variable cost tasks. So you know that the structure of the tree, but you don't know the cost of the tasks. And this leads to what their algorithm is work stealing or task pulling. That is, you randomly pick a processor and steal from it when you run out of work. And Showman Chakrabarty, who was a student of mine, proved the opposite, which is if you use randomized pushing, it's also optimal with high probability. Both of these results are high probability results and are relying on the previous balls and bins argument that I talked about before. And there's the first result, the work stealing result, is used in is in the Silk runtime system, and there are a few more slides that I normally present on Silk. I think in the interest of time, I'm not going to do those today, but that's certainly a programming model. It was actually there was started a company based on Silk. It stands for the parallel language in the C ilk, so it sort of feels like C, but it does have a little bit some extensions for parallelism built into C. And then what that company was Silk Arts was purchased by Intel at some point. And so that has made it into some of those ideas have made it into the OpenMP implementations, for example. That's why you see some of those kinds of features already built into OpenMP. Now, in Chakrabarty's case, he was looking, first of all, at distributed memory, whereas Silk was focused on shared memory, and was also, as I said, looking at this idea of randomized pushing. So what's the difference between pushing and pulling? Well, pulling tends to be better for locality, in fact, significantly better for locality, in the sense that you mostly execute locally and you don't steal something until you run out of work. However, pushing actually balances the load more quickly. So if you've got a large machine and you start out with a single node at the root of your tree, and all of the processors, let's say you've got 128 processors, 127 of them are all randomly trying to steal to find the one processor that has some work, or maybe a few processors if you've gotten a certain way through the computation that has been then spread out. Whereas randomized pushing tends to give you more, from an experimental standpoint, gives you a better load balance more quickly. But it is worse for locality. So you typically need chunks of work that are very large and don't require that you move too much data associated with them, at least relative to the amount of work that you're going to do. And just to show that this actually did work, even the randomized pushing worked, and these two are two different problems. Now, this is an ancient machine, the CM5, but this was a Grosvenor basis computation, which is a symbolic factorization algorithm that had a dynamic load balancer built into it and a eigenvalue computation recursive bisection algorithm for computing eigenvalues. That is, when you have a particularly badly load balanced case happens when the eigenvalues are very clustered. And so even though this was running on distributed memory, it actually did scale reasonably well. Okay, so the last case to talk about here is when I've got a more general directed acyclic graph of tasks. And this is an example from a linear algebra problem of Cholesky factorization and what the task graph looks like. So there's sort of a fan out phase where you're generating a bunch of tasks at the top, say upper left of the matrix, and then at the lower right, you're getting a bunch of incoming, you're waiting for a bunch of tasks to complete in order to do that work at the bottom right of the matrix. There are lots and lots of pieces of DAG scheduling software. This list, I'm sure, is far from complete, but it does have some examples of the different kinds of DAG scheduling algorithms. Some of them, like in Silk, it does handle things that are a little bit more general than a tree, but it's basically a fork join graph, and that is related to, in part, to the underlying theoretical results that are only done for a graph that has a particular structure that looks like a nested set of forks and joins. It doesn't have sort of one arbitrary task up here that's going to be have a dependence with something that's at some other part of the graph below. And just to give you a sense of how big these tasks can be, and this is from Jack Dungara's group at University of Tennessee, who built, as I mentioned, one of these, some of these, actually multiple schedulers for scheduling task graphs, starting with shared memory and then eventually moving on to distributed memory. But in the shared memory case, but just looking at the size of these graphs, if you've got an n by n matrix with b by b blocks, then you end up with, this n over b value of quantity cubed. So you can end up with a very large DAG to schedule. And so creating that DAG sort of upfront and then trying to schedule the whole thing, this NP hard problem, even with heuristics, tends to not be very practical. So they're looking at their techniques for scheduling, say the frontier of the DAG, which is also what Silk is doing, is looking at that particular frontier of active things and scheduling them. Although Quark is doing it, looking at more at the DAG structure, whereas Silk is not. It's just executing an arbitrary set of P things. And a project that I worked on years ago in UPC with Perry Husbands, who was at the lab at the time, was looking at LU factorization and doing this dynamically. So this is a dynamic, so a static assignment of the tasks to the processors, but a dynamic set of scheduling of when the work is going to get scheduled. This just gives you another sort of pictorial of how the work unfolds in something like LU factorization. But the other thing I wanted to note here is that you can end up with problems we call memory deadlock, where if you're trying to overlap the communication and computation, and so you allocate memory for tasks that aren't yet ready to execute so that you can make space for the incoming blocks, you can then run out of memory for the blocks that are on the critical path that may then be dependencies of the task that you're waiting on. And so this was actually a problem that he ran into in the first version of the algorithm and had to then implement a more memory constrained look ahead algorithm. So this comes up also more recently in UPC++ and SIMPAC. I think I might have mentioned this in the PGAS lectures. I think the last thing I just want to mention is about tasks with communication. And as I said, if you know what the communication graph looks like and you know what the tasks are, you can actually run some kind of a graph partitioning algorithm on them. But if you are in the general case, you're going to have to do something much more dynamic. So I'll just mention then a system called Charm++, which is used for load balancing these kinds of computations. It is based on the idea of, it's first of all looking at iterative computation. So things that come up that are going to repeat the same patterns over and over again of communication and computation. That is the cost of the communication, the cost of the computation, and the set of relationships between the different tasks are going to be repeated iteratively. They over decompose the work into chunks of work called chars, and those chars are going to have some data and some computation associated with them, and they will be moved around the system for load and balancing. So, how are they going to assign the load, assign these chars to the system when they are being created dynamically? Well, basically, they are going to use this principle of persistence. So they could take user hints. They can try to just sort of estimate what the cost of things are going to be. What they're going to do is record information about communication and computational costs, and then assume that there's some kind of higher level pattern that says a particular char, which is going to execute, say, multiple times across different iterations, is going to have a similar communication pattern and a similar cost to the previous iterations. And this is used especially in a very well-known molecular dynamics code called NAMD, but also in another large set of applications. And so what they do in the runtime system is they'll look at the execution, they'll instrument certain set of the time steps and collect information about how load balanced things are. And then they will aggressively load balance things and then execute them. Or they'll also use what they call refinement load balancing. So the first time they load balance, it might be quite aggressively moving chars across the machine. But as it executes, it continues to instrument things and then do a little bit of sort of refinement of the load and balance if there are problems. So that might be just moving things around to nearest neighbors or something, but not major rebalancing globally. And it sort of uses this hierarchical schedule, which helps with the scalability of the load balancing algorithm itself, and also takes into advantage the topology of the underlying machine as well as the topology of the execution. And these are some results from NAMD, the molecular dynamics simulation. And this is actually not from the UIUC, which is Sanjay Kale's group where Charm++ is developed, but from Mike Normet at UC San Diego, director of the San Diego Supercomputing Center, on a astrophysical simulation called ENSO, and using Charm++. And so it scaled very well, as you can see, up to 10 to the 5th cores. All right, so just to summarize, there's often a trade-off between moving things around for load balancing and the cost of locality. There's a lot of algorithms, papers, and software on load balancing, and it can be a little bit hard to navigate, but I tried to give you a few different principles, so questions to look at if you're looking at one of these papers. Is it addressing a tree? Is it addressing a DAG? Is it addressing communication costs for distributed or shared memory, and so on? And so all of these different things can come up. Do they care about locality? Is it something that they're ignoring in the analysis or in the experiments? Are they choosing problems where, like, dense matrix multiply, the compute to communication ratio is very high, or are they looking at things where you really need to worry more about moving the pieces around because the ratio of communication to computation is low enough? And I think one of the open questions is going forward is going to be, we are seeing things like dynamic clock speed scaling also creating more heterogeneity in processor performance, and whether that will require more dynamic load balancing going forward than we have had in the past on our HPC systems. So, oh, and the last thing I wanted to just mention, I know there's still a few people who haven't quite settled on their final project. Hopefully you've submitted your proposal, but even if, whether you have or have not, if you still have questions about whether that's the right project to work on, one thing that we think would be a good project would be taking one of these programming models, whether it's something like Charm++, UPC++, Chapel is another one, and doing some set of benchmarking and analysis of both how usable and how performant those are across some set of benchmark applications. And let's see, there's a couple of questions here in chat I will try to answer. So let's see, going from back to forward, I think that Aydin answered the earlier one, and Jim was asking about both pushing and pulling by idle processors. So yes, in one of the work task queues that we built in a library called Multipull that was using both pushing and pulling, and had what are called low water and high water marks. So if you got too close to being out of work, then you would start stealing. And if you kept track of sort of the high water relative to other processors, you could start pushing aggressively. And those were things that could be set by the user of the task queue. And that was in a distributed memory setting. So both of those things can make sense, even together. Although I think the theoretical results around them, I don't know actually whether the theoretical results apply to the combination. Probably they do. All right, thanks very much, everyone. And let's see, there's more information, I think, coming out about poster sessions and things like that. And just make sure you're watching Piazza. Anything else from anyone that anybody else wants to mention? Okay, we'll see you next time. Bye.